Hey, yeah, you guessed right. We're just doing a laptop lab again. We're doing a lot of simulation today and doing nodal and mesh analysis. So yeah, if you want to grab a laptop, you can also work with somebody on it if you like. So you don't have to have your own, but you do all have to master this stuff. And there's going to be a lab practical next week where you have to develop a breadboard on Tinkercad. So you have to implement a circuit on Tinkercad, kind of like what we're going to do today. And the more practice, the better. So if you want each do your own, that's fine too. So anyway, I handed back the test, but I didn't hand it back yet. I said I was going to hand it back to myself. Anybody else? Anybody else? Come over here. Got to give anybody two tests? I think two. And I have your sheets. Yeah. So what I'm going to put a name on there. Good. So first order, let's talk about the test. And if you are wondering where you might find the solutions, there is a solutions link on Canvas. Which is under course resources. And these are the solutions sampled from Mark's test. Thank you, Mark. I didn't ask permission. Hope you don't mind. The scores on the multiple choice section were fairly good. Here's your test. Okay. Oh. There were a couple sign errors that people made, like -2 volts instead of 2 volts for this one, because maybe they didn't properly do KVL. Or they didn't realize that the current source is going down, so therefore I3 is going to be flowing backwards. Or they might have got 4 volts here instead of -4. Again, Vx is a node voltage here, so you know, whenever you see something like this, and I noticed this later in the test, a lot of people were having problems with this. When you see a node label there, what does that mean? It means that it's like you're hooking up a voltmeter, and the plus lead is here, and the minus lead is here. That's interchangeable. So KVL says that Vs plus Vx equals 0. Therefore, Vx equals minus Vs equals -2. And that results in VO equaling -4. Okay, so be aware of that, those of you who missed that. And if anyone wants to ask any questions on those, now's your chance. Number 6 is an extremely easy problem if you know what you're doing. If you don't know what you're doing, it's extremely difficult. Or if you have some confusion. So there were a lot of points lost when people kind of were floundering. Basically, I'm looking for a couple of things. You can see it's actually, let me zoom in on this thing. It's actually a fairly simple circuit, right? And the thing is, even these simple circuits can really confound us if you're not comfortable with the rules. And when you look at this circuit, there is a obvious sort of node here where two currents are coming together. And so you can do KCL at that node if you call that A, in which case you got 10 amps flowing in, you got 2 VO, that's a current flowing in. I know it's weird, but it is a current. And you have some current flowing out, perhaps you want to call that I3. So you now have an equation for I3, and then you can substitute that because Ohm's law, and in this case the way Mark drew I3, that's passive, that's active sign because the current is going into the minus side of that resistor, labeled from the VO perspective. So VO has to equal minus I3 times 4, or R4. That means minus the value you just figured out, minus 10A plus 2 VO times 4. And then that equals, that gives you a nice equation. So that basically allows you to solve for VO. So you get this nice equation there. So basically VO equals minus 40 volts minus 8 DO. So 9 DO equals minus 40 volts. VO equals minus 4.44. And that's your VO. Now the other part that people were kind of running into problems with is calculating the power of the dependent source. That's this guy right here. If you want to calculate the power, you have to find the voltage across it. Maybe you want to call that something like Vx, or in Mark's case, he called it, well, he didn't call it, he called this voltage V1, and he found out what that is, and then he called it just V current for the current source. On many of you, I marked it up and just call that one, just call it Vx. You don't know what that is. That's an unknown. You don't know the voltage drop across the current source. The voltage drop across the current source is most definitely not V0, as a lot of people actually did. It's not V0. That is a current source that's controlled by V0. It's pumping out to V0 of current, but the voltage is unknown. So you have to find the voltage using KVL. Now that you found I3, you can find the voltage drop across those resistors, do KVL, and come up with a value for the current source voltage, which is 11.11 volts. You can then find the power, and the power is greater than 0, so therefore the circuit, the dependent source is absorbing power. everything in chapter 2 is embedded in that one problem, and it's all tangled together. You have to get those things sorted out properly to be able to solve this. If you're stumbling on a few things, if you're doing KCL when you mean KVL or vice versa, then it's going to be impossible to solve it. You have to get those things clear. So that's a good one to practice. Maybe later, if you just hide the solution and do it again after having seen the solution, this might make a lot of sense. Number 7 is fairly straightforward, but there's a few pitfalls. A is a voltage divider, and you've got a parallel thing there. Like, how do you deal with that? That shows up from time to time in our homework. So that's the thing where the voltage drop across a parallel set of resistors is the same. You just have to find the parallel resistance of that. So that is equal to 6 parallel with 3. That's equal to 2K. And that allows you to plug in the voltage divider formula to find V1 of 4 volts. But you have to do that on the parallel combination. The individual resistors 6 and 3 cannot really be used in the voltage divider formula. You have to combine them to find the series, effective series resistance of those two in series with the others in that path. And then B is a current divider problem most easily, although people use KVL and KCL to solve it. You can do that. But if it's a current divider, you just have to say, well, this path has the same current and it has a net R of 15K. So Mark used the current divider formula. He found G12, which is the combination of those two over the sum of the two G's. The G's are the reciprocal, so this is 1 over 15. And he kept it in ohms, and that's fine. You know, 15 is 1 over 15,000, so that's 10 to the minus 5, 6 times 10 to the minus 5 Siemens, and then that is the reciprocal of the sum of the reciprocals. So giving you 4 milliamps and 28 volts altogether to do that. Any questions on those? Or the previous one, I kind of blew through that. Any questions? Anybody want to bring up on those? It even has a active sign convention, Ohm's law thing. So there's just a lot of issues with that problem. Definitely, a lot of people kind of got hung up on. This one wasn't as bad, but last problem is nodal analysis, and Mark correctly labeled these nodes. So another issue with nodal analysis is what do you label the node voltages as? Some people said, all right, I'm going to call this like V1, V2, V3. Don't know what these are. But when you see a voltage source attached between a particular node and ground, this is not or a voltage label, like a voltage label across this thing, right? This is something we run into a lot, and these guys here, these guys are not floating voltage sources. These guys do not do a supernode for those guys. That's inappropriate for this kind of circuit. These are just regular voltage sources attached to ground. And so a lot of people just went and did a supernode thing, which made them really kind of messed up. Because that's not when you do a supernode. You do a supernode if you have like a voltage source strung up, like say between here and here. Suppose that was a voltage source. The point is neither side of that voltage source is connected to the reference node. Therefore, it's a floating voltage source. Therefore, you use a supernode for those kind of problems. You don't use supernodes for voltage sources that are attached to ground. This was supposed to be relatively easy. But this is new stuff. And for me, it's like, oh my gosh, this is so easy. But when you see it the first time, it's not so obvious. So although this hopefully wasn't the first time you saw it. So the realization, when you see a voltage source attached to a node, you don't need a separate variable V1 for this. You just erase V1 and say, well, that node voltage since I've attached a voltage source that has a voltage of 4 VO across it, that node voltage at that upper left corner has to be 4 VO. This node voltage here, some people labeled that V3 or something. Oops, I didn't. That's already done it there. Is also attached to a voltage source. So that voltage has to be 3 volts because you got a 3 volt source connected to it to ground. It's maintaining a 3 volt energy level at that point. And then finally the VO here. In other words, the VO here becomes the node voltage in the upper right corner of that circuit. So you don't need another variable there, right? If you have too many variables and your equations aren't actually defining them all, then you can't get the right answer either. So this only has 2 unknown node voltages. It has VO and what Mark has called V2. These are the only 2 unknowns. V1 is known as 4 VO, and this thing here is 3 volts. So that's a key part of the problem solution is figuring out what these node labels should be, right? You can't just name them anything if there's some constraints going on there with voltage sources. You got to name them after the voltage source that's tied to those nodes. But once you do that, then it becomes very mechanical. You do a node equation for, this looks like V2. A node equation for VO. Somebody, Miguel, there's an online, Miguel, he actually did a voltage divider formula. He saw this as, VO equals V2 times 2 over 2 plus 5, 2 plus 3, sorry. So 2/5, so it equals 0.4 times V2. So he got that equation real easily, but the nodal equation, typical nodal equation would be, V2 minus VO over 3 plus 0 minus VO over 2 equals 0. So you put those together into matrix form, and that's what I was looking for. Some people actually just went ahead and solved for them, which is fine. In the future, when we do this, when we come back and do this with complex numbers, it's going to be really easy to just put this in matrix form. You're going to be doing that today in the lab. So everybody will have a good experience for how to do that. Any questions? Anyone have any questions on what was covered? Whatever. Okay. All right. Well, the homework for mesh analysis is due today. And we are doing a lab involving nodal and mesh analysis. So I also pointing out there is a lab practical next week, which is going to be done. You could do it in class if you want, or you could do it at home, but it's going to be done involving, resistor color codes. That's pretty trivial. You should all know this by now. Although sometimes the colors are hard to tell on the screen. And a breadboarding problem, that's the main thing. You should be able to build a breadboard. And since it's less cumbersome to do it on the simulator than in a real breadboard, I'm asking you to do it in Tinkercad, although I suppose if you really don't want to use Tinkercad, you could do that, but it's hard for me to tell if there's an error. On a real breadboard, it's kind of hard for me to read those photos people are putting in, so it's easy for me to look at a Tinkercad circuit layout to see if you got it laid out right. But, another option is if you want to just build it, I might think about this. Maybe if you want to just do it in the lab and build it and demonstrate it in front of me and just not have to worry about taking it home, you could do it that way too next week. The lab next week is sort of an optional extra credit lab. We're going to be playing with diodes and transistors. It's not a topic that's in the circuits class. It's not in the Engineering 12 class, but it's an interesting topic just because they're really useful and important devices in electronics. So that's coming up next week. And We are doing lab 5 today, nodal and mesh analysis. You might want to have this fact page up here. There are so many questions people have on this lab. This lab unearths a lot of uncertainty that people have. It really focuses on it really focuses on the layout of a circuit. You know, there's some tips here on how to lay out a circuit. You're going to be asked to lay out a circuit that looks something like this. A good suggestion is to look at your breadboard and decide where you want to put the nodes, where you want to put the reference nodes. And there's more than one way to do it. That's where it sort of becomes an art form. But if you're trying to build a circuit that has 3 nodes and a reference node, and the 3 nodes are kind of listed across the circuit, 1, 2, 3, you might decide to kind of put them in your breadboard, something like that, right? And then this becomes the place where you attach all these 3 components to, and some additional tips. Laying out a breadboard is an issue that some people really struggle with. So dive into this and think of it as an opportunity to finally clear it up. It's really not that hard. Remember the way breadboards are connected. Each of these, the reason these are circled is because each of these 5 pins are what? Sorry, Mark? Yeah, they're a single node. They're electrically connected. There's a metal clip underlying those 5 pins that is going to, if you put 2 wires in that clip, they're actually connected to the same, they're connected to each other. Put 5 wires in that same clip, they're all connected to each other. And they're not connected to the one right next to them, right? Or the one 10 rows down. And then anything on a continuous line in your breadboard, be aware of that break. If you have a break in your breadboard, you got to be aware of that. So there's not a connection between those 2 sides. But anywhere you see a continuous line on these side channels, those are all connected. So this could be a reference node. That means any wire anywhere in this row here, in this whole channel, will be connected. But it's certainly possible to tip things differently. Have this be your node 1, this be your node 2, this be your node 3. It'd be kind of weird, but you could do it. If you want to do a strange one, that's fine. You kind of experiment today. And I don't think we're doing it. Well, let me see the lab here. You all got your lab in front of you, right? You got the lab handout? It was over there if you came in late. Did you get a lab handout? So this is the actual lab. I guess I am asking you to build this thing in on a breadboard too. Wow, we're going to be pretty busy today. I'll have to pull over the circuit kits. I guess I wanted you to practice building the circuit in Tinkercad first before you put it on your breadboard as additional practice, so that you'll be ready to take the test, the practical test next week, in case you haven't practiced with Tinkercad. I'm now sort of thinking that, if you just want to skip that and do the test on a real breadboard, that's okay. I don't really care if you master Tinkercad per se. I think you can demonstrate it fine in front of me using a breadboard. But if you want to, if you want to take the practical on your own time at home, you can do it in Tinkercad. That's fine too. So in the interest of time, if you want to skip that Tinkercad step, you can, but it might be kind of fun to try it. It's a good, if you're not certain about how to do breadboarding, it might be less intimidating to do it in Tinkercad first, because you're not going to damage anything, right? You can hook up your circuit just fine that way. And then however it looks in Tinkercad, then you can build the same thing on your actual breadboard. And here is the data sheet. So this is the circuit that you're going to build. You notice it actually has 2 voltage sources. That's why you have 2 power supplies in your circuit kit. You're going to have to hook both of them up to your circuit. You cannot use the same voltage source and wire, you know, both of these things back to the same voltage source. You have to have 2 separate ones, so you have to have 2 of those breadboard jacks in place. In Tinkercad, you're just going to hook up 2 different power supplies and connect them into the circuit between the nodes the way they're shown. And the first step is to build a circuit model using whichever simulator you use for Lab 4. That means for everybody except for a couple folks, that means Circuit Lab. So you can log into Circuit Lab using one of those accounts if you want, or if you use your own, that's fine too. And you'll include a screenshot of that. So you're going to simulate it, and this is going to tell you what your node voltage should be at the second node there, node 2. But that's going to be done in a simulator. Then you're going to do it on a breadboard. And then you'll be doing some going to record those voltages, and it's asking you to build the circuit on the breadboard. So basically, it's sort of asking you to first simulate the circuit using these numbers, and then measure your actual resistor values and your actual voltage source values, you know, from your real kit, and then change the values in your simulation so that they actually match what your kit says. So then you'll actually be closer to what your kit's going to show you, right? So when you actually finally build it on your actual breadboard, your circuit model and your breadboard circuit should be very close together. They should have very little error between them. So that means once you build your breadboard and then you measure your node voltages and compare them to the voltages in your model and your breadboard, if there's a difference of more than 2%, there's something weird going on. Maybe your wiring is screwed up because you've modified your model to closely imitate the values of all the parameters in your circuit. So they should be very similar. So look for an error. And oh, look at this. People in lab had 3.5% errors due to wiring problems that were resolved when corrected. So if you get an error of 3.5% in those numbers, that's significant. You should figure out what's causing that and get the errors to go to 0 if possible, close to 0 as you can. Oh, I guess the third part is building it in circuits.io. And you know, you can say part 3 is optional. Why don't you put optional in there? If you plan to do the practical next week in the lab, you can just you don't have to master circuits on Tinkercad, so you can make that optional. Oh, and by the way, everywhere it says circuits.io, that means Tinkercad. I haven't changed that. I got to mess that. Got to redo that. All right, now the last part, you might actually not, that's why actually it might be a good idea to make part 3 optional. Now I'm sort of thinking that we don't want to take too much time away. Because part 4 is where you got to do the same, you got to derive all those variables using nodal and mesh analysis. So that same circuit that you just did, you're going to, there's some paper there for you to derive the nodal equations. There's some space on your handout. There's another space on your handout to do the mesh equations. Using these labels for the mesh currents, derive those things. And then at that point, you've looked at this circuit 3 ways from Tuesday, so it's all going to be hopefully consistent, and you've reached the same answer for all these 3 approaches: a simulation, a breadboard, and your circuit analysis tools using nodal and mesh analysis. And that's the whole lab. It's just looking at this one circuit. If you do want to tackle a more challenging circuit, you can try doing this one, which, of course, you can't build it. So nor can you simulate that. Well, you can't simulate it in Tinkercad, but you can simulate it in Circuit Lab, right? You can simulate it in Circuit Lab and then do the node and mesh currents in a similar manner from your previous work. You've got a dependent source there, so you're going to have to treat that a little bit differently. In case you forgot how to solve systems equations in MATLAB FreeMat, there's a little appendix here you can use for that. Any questions before we get going? Cameron?
On the data sheet, it wants us to have the matrix solution, but do you want us to have like the whole derivation?
No, I don't need the whole derivation, just the matrix. You know, if the numbers aren't within 3.5%, you're going to have to redo your derivation. So I'm not going to look at the derivation. I just want to know that you got the right number. Yeah. Okay. Any questions? So everybody, the first step basically is to do the simulation, right? First step you're going to do is simulate this guy. You can use PSpice, you can use Circuit Lab, but you're going to start with a model of the circuit, and you're going to use the login access to, if you're going to use Circuit Lab, the login access is on the main page. Using one of these two shared accounts. So they are right here. And do me a favor, and when you make your circuit and you want to save it and name it, don't put your name on it, just put your initials. I'm afraid if someone looks into my account and sees everybody's names on the circuits, then they're going to know that it's a shared account. I'm kind of paranoid that way. But if you just put your initials, like, you know, Lab 5 DT for David Tuhig, then that just seems like a friendly variation on the circuit you're trying out. A bunch of different kinds. And nobody has to be the wiser. So everybody clear on that? Thank you. Keeping costs down for everybody. Okay, so grab a laptop or join somebody who has a laptop and start simulating, and I'll bring those circuit kits over. The question on whether the wiring is good, and we've got a circuit. Let me get this writer here. You're trying to build this circuit right here.
Yeah.
And you've got your nodes laid out here. So you've got your reference node on the bottom, that's really nice. You've got a 1K. You have a voltage source there, that's going to be a positive and minus. Another one here, that's going to be positive and minus. And your 470K, your 470 resistor is not 470, I think. Have you measured that?
Yeah. Wait. Oh, I think I put the wrong one in there.
Yeah.
It's supposed to be the purple.
Yep.
Purple one.
Yep. Very easy to mess up.
Okay.
Mm-hmm. Otherwise, looks good.
Okay, cool.
Very neat. I mean, that's a really nice layout, right? It's different from what I showed you, and it really gets the job done, and it's really easy to see
Cool.
how it correlates with the real circuit. Good.
Okay. When we do the practical, are we going to have one of these available, or?
Yeah.
Okay.
Well, I
I'm
mean,
gonna
you
memorize
can Google it.
Well, like, but during the practical thing.
Yeah.
allowed to
You can have it if you do it in the classroom. Yeah.
Oh,
you can have
okay.
it.
All right.
Yeah. Any other questions? Sorry.
Oh, I actually do have a question. For the, how do you want us to take the photo? Just with like our phone? Phone?
The photo
The
of,
actual circuit.
For step 7.
you mean of the simulation
No, the actual circuit.
of the actual circuit? Yeah, use your phone, and you know,
Upload it.
Yeah.
Okay.
Take a close up too, so I can see the wiring if there's any.
Yeah, you want two
Issues?
photos, one
Yeah.
of V2 of the voltage of V2, and then the other one of the close up. Right?
Uh huh. Close up. Yep. Good.
Okay.
Questions, anybody? Yep.
Voltage or resistance and voltage, I guess.
Uh-huh.
Do we measure it like while it's in the circuit?
No, just measure it with an ohmmeter and with a voltmeter.
So you just like measure the difference across these.
Yeah.
Yeah,
Show me that.
two
Yeah,
of them.
measure the distance across
Just do it with two of them.
across those. Yep. For both of them, and keep track of which one's which.
Right.
Pace is different. Any other questions? Questions? Anybody? Questions? Sorry?
Yeah.
Oh, the lab handout? Yeah.
It's a word problem. It's not a circuit problem.
Yeah, that's okay. Any problem is fine.
When I type we, it goes in the other column.
You're using WordPad.
You just open it in Google Docs.
Yeah, you're typing when you type what?
Like when I type in this box, it goes in this one.
Yeah, WordPad probably doesn't have the. Yeah, I think you have to use Google Docs. Why don't you open it in Google Docs?
Yeah, I'm gonna go ahead.
If the way we connect the batteries are okay in terms of damaging.
Okay, so here's your circuit.
So this is V1. So this is V1. That's V2. That's V3 or node 3. Node 3, 2, 1.
Are they upside down? Wait, 3, 2, 1.
Yeah. Sorry. No, 1, 2, 3, and then R4 instead of on top, we have it on bottom. Going from V1 to here, looping around, and then that's R4 up to V3.
And then we made the negative right here, the reference node.
Yeah. And this is VZ, and this is VX.
I'm really confused here.
So is this a bad way to set it up?
I think so, but let me. I might not be getting your point. So this is what are the nodes again? Is this a node here?
That's 1.
That's
that's
node
node
one?
1.
Okay, but node 1, and this is 470,
Yes. 465.
and this is your reference node.
Yes.
Okay. All right, and this is node 2,
That's node 2.
and 220 going to the reference node.
Yes.
And you have a resistor to node 3, which is going through 12 volts, which is positive is the orange.
Yes. That's the.
It'd be good to actually use a dark color for ground, but that's okay. And so that's this source going plus 12 to ground. And then you have R4, which is 1K going to back to node 1 with this wire. The reason why you broke it there, just 'cause it wasn't long enough.
Huh?
Why there's 2 wires there. You could,
Oh, I could have just connected that yellow one up here,
yeah.
but
Okay.
yeah.
Or you could connect this yellow one right there. Either way. And it seems okay. Let me just check the polarity here. So this is node 2 to node 1. Is this
Positive.
orange again is positive? Okay. Yeah, it seems okay. But it is confusing. Do you agree?
No, actually I don't. But
I mean, there isn't really a. I mean, it's topologically it's correct, but it doesn't visually
right.
allow tracing that way very easy. Like if I was going to grade this, I'd be like, "What did they do? This is all confusing." It looks like I need to make the circuit go like this, but then that's not true either because you know it doesn't line up that way either.
Right.
So there isn't really a way. Now it's okay, and in general, circuits are not going to conform to the way their schematic is laid out. But in this one, you could have done it, and in fact. If you look at Matthews, I hit a really good. You can see another way of doing it. Can I show them your screen?
Yeah, I put the wrong thing.
So when you look at how Matthew did it, and everyone can look, and if you're trying to figure out layout, here's a good example. It doesn't matter. You don't have to change yours, but you can kind of see how you can do it so that the circuit actually agrees really well to the schematic. So here is his circuit, and he's got the R4 going across the top. You can see on the screen up there. You see that? That's the R4. It aligns really well with that R4. He actually inserted his voltage sources right in there because there isn't really a need to have the rail there if it's only inserting at 2 points, which is different than what I've told you, but it was a good leap there, right? And then he has the 220 coming down. This is the reference node kind of going across here, right? You can kind of see that. And then this is the 470. So when I look at this, I can say, yeah, everything is in the place where it belongs. And it lines up perfectly. There isn't really a right answer, but you can see how some approaches can be easier to debug. When things don't work right, you got to track things down. His circuit would probably be easier to debug than yours.
Okay.
Yeah.
So if it's possible to make it look like the schematic.
Well, it's okay, and if you can make it work
Yeah.
and you're comfortable, that's okay. But when you run into problems, like when I see people that are really confused, there is no rhyme or reason to what they connect. And it can help to really visually orient the circuit to the schematic.
Okay.
Because that can really help track things down. Yeah. Looking at the circuit. You've got the wire going up there, very nice. You spread it out more, which is good, helps a lot. You've got the white wire going to minus and the gray wire going to plus, which it's not incorrect. You've wired the circuit properly, but it's non-standard. You know, the convention is to have the dark wire going to ground, or the low potential, and the light-colored wire going to plus, right?
So I would switch those.
You switch the white and the black, but there's no reason electrically why this won't work that way.
But if I just unscrewed this and flipped it around,
you could.
according to convention.
You could, but no, you can't. Wait.
I
Well,
just
you'd have to
mean-
unscrew it, flip around, and then take it out, the whole thing out, and put it back in again. Because then you would have basically the gray wire going here and the white wire.
Oh.
Because you want the plus to go here. That is correct the way you've wired it. But it's better if that wire is white and
Oh.
the wire is gray.
Yeah.
There's no reason why it can't be where they are. But
Gotcha.
it is helpful for debugging and to always have that kind of assumption. That's what people are going to do. There's your R1 going to ground. The grounds are jumpered across, which is good. Here is your 220 going to node 2, 100 going to node 3, and power going to and then 12 volts to there, and then there. Yeah, it looks good.
All right.
Looks great.
I also have some pictures from last week's lab.
Because
Okay.
I was when we're doing it on Sunday, but I didn't have access to those pictures. So
Uh,
we turned it in. We
Okay.
turned in the lab just without the pictures of the first two circuits.
okay, if you go in, I think you can post a submission comment, and you can attach the photos to that. That would be helpful. Yeah, best place to put it otherwise.
And,
it'll
and if
probably
not,
get it.
maybe like
So for this one,
It's gonna be more complicated.
you've got it kind of going this way, yeah. So this is the 1K going on top. That is your R1. This is going to, oops, I'm going that way. Sorry, that's your R1. Now I see a problem here. Maybe you can tell me there's something going wrong with the way these two resistors are mounted. Can you see what the problem is?
No. Wait. Oh, they're in different holes? Like,
Sorry?
this one is like in the wrong hole. It should be one down.
No. The problem is both ends are wired to the same node. So this is not two separate nodes here. This is actually one. This whole thing, because these 5 pins are connected to the same metal clip, right down there. Put that lower. So these things are connected together. So it's like the other end of this resistor is connecting to node 1 as well on here, like both ends. It's like you've got this going out. In fact, you can do it with a pencil here. It's like, what is that? Can you get that going? You just use it like that. It's like you have, like that. It's not going to a different node.
Okay, then.
Because these are electrically connected. And then this is, see, this guy is supposed to be connected on this side, but you've got it kind of routed on the bottom. It's going to this thing. So really, this is, see, this minus is supposed to be connected to node 1, but your node 1 is sort of mismatched. And so is your node 2. They're not really done properly. And then, yeah, so why don't you reconfigure that? You're going to have to do some steps here. I'd rather not tell you so you have a chance to kind of redo it. But let's look up here. You've got, this is your node 3. And your node 3 is going 100 ohms to node 2. Yeah. But then, yeah, that's okay. Your resistor is going all the way to node 3. But wait, is that actually, yeah, these are connected here because they're going into the same row there. So that node 3 is okay, but nodes 1 and node 2 need to be reconfigured. Yeah, let's give it a shot. So online people can see all different ways to do this. So Daniel has a nice, neat layout. It's different. So let's see how we can verify it. So we've got this.
So this is like my node 1.
This here looks like node 3, right?
Oh, yeah,
Wait,
yeah.
This is node 3.
Yeah.
This is node 1.
Yeah, exactly.
And then this must be node 2.
Exactly. Yeah. And
node 2 is going to plus 12 relative to, let me see here, but wait a second. This node 2 is, well, this point here is going to ground, right?
maybe
So you have
node 2
the
is
plus
one.
going to red.
yeah, this is node 1.
Wait, that's this is node 2. Yeah, node 2 is going to the 12
Yeah.
side. Good. And then the minus sign is going to node 1, right? So yeah, so it goes. So this is your, do it at an angle here, let's see better. So this is your node 2, right? Oops, this point here is your node 2.
Yeah.
And it is connected through this wire to the red, which goes all the way down to the plus side of this voltage source. And the minus side is going into node 1, where the 1K connects with the 470, right? Yep. And the other end of the 470 is going to this, which is your reference node. And you have the, let's see, so the 220, wait, and then the node, wait, the 220 ohm is here, also going to ground. Good, okay, that's good. 220 also going to ground. And then you have the voltage source here going from node 3 into the plus side and coming out back to ground. I think that looks good.
Okay.
Yep, and this is your reference node there.
Yeah.
Yeah, it looks good to me.
Okay.
Mm-hmm.
Thank you.
Yep. What's the spec?
That is mine.
Yeah, it is. Slinky. Okay, so you've got, this is your node 1, and you've got a plus minus. This is reversed.
Okay.
Now you can see how the plus is going here, right? The plus is supposed to be on node 2, right?
Plus is on.
Can you grab your hand up?
Yeah.
So like David, your
I
wires
didn't even check it.
are the barrel jacks are color coded incorrectly,
Oh,
and it's not electrically incorrect. It's just stylistically incorrect.
okay.
We tend to want to make the lower potential one be a darker color,
So
and the higher potential one be a hotter color.
minus the dark, plus light.
Yeah. So, and when you do that, you'll see, because see, this is asking you to have the high potential side to node 2. You've got the
Yeah, I didn't even check that.
minus side, which is a low potential side, going to node 2.
Okay.
So you have to flip that.
Okay.
You could just flip it, but I would
Yeah,
recommend changing the wire
I'll
colors
swap
too,
the
because
wires.
that will make it a little clearer. And then 220, you got the is that a 1K? I think you're yeah. This is the wrong resistor value.
No, it's not.
Yes, it is.
That's red.
Yeah, but the color code for 100 ohms is brown, black, brown. It's 1, 0, and 1, 0. In other words, brown for 1, black for 0, and brown for an extra 0. This is 1K right here, and this is 10K. That's orange.
So
Brown,
that's-
black, orange is 10K.
You're talking about this
So
one?
this resistor that my finger's on right now should go here. This should be removed, and you should find the brown, black, brown
Oh.
color bands to go right there.
One second.
This power supply is also wired backwards. Notice the low potential side is
Yeah.
going to node 3, which should be the
So
high potential
You're
side.
saying brown, black, or brown,
Black, brown. Yep. Because you want to take 10 and multiply it by 10 to get 100.
Oh, okay. Yeah, that's where I was confused then.
Okay, so you're going to switch those polarities and colors, and then switch that resistor to there, find the 100 ohm resistor, and then I think, so these are, this is a reference node, so that looks good. And those are connected across, so I think otherwise it looks good.
Okay.
About 3 changes to make. Has anyone got coherence between the model and their breadboard yet?
Yeah,
Did you?
yeah,
How close was it?
really close, like under 1%, like
Good.
really.
Oh, that's really, yeah, that's what we want to see.
Yeah.
Yeah, those are great numbers.
Yep.
Good, now you can do the nodal and mesh analysis.
Yeah.
Yeah, that's the hard part. So made some changes. And now you have the 470, that is ground, your reference node. 470 is going to node 1. You have the
That's what
right
still-
polarity. This is going, what is that? That's going to, that's your node 2, I guess.
No. That's node 4.
This here is your node 2, right?
Yeah.
You might want to try straightening out that wire. It's kind of curly-cued at the end there. You might not be getting a good connection if it's not going in all the way.
Okay.
Yeah, see, that wire should be straight if possible. You know, when you have those weird bends in it, you see that curly-cue there. You're taking away some of the wire that can go into the clip, so that might give you a weak or improper connection. And you have these pliers here, which you can use to straighten out. That's a good skill to kind of just have to get used to. And then you have, so that's your 220, the voltage source. And then you have your 100 ohm going to there, which, yeah, I would, my recommendation is to change the color so both of these have the white on the plus side and the gray on the minus, just for consistency with the convention. It's a convention, right? That the dark color is gray, I mean, the minus the low potential is a darker color and the high potential is a lighter color. It will help you in the future to kind of know that. And when I look at that, it kind of, when I see the colors, it kind of makes me worried, but then I have to look here and I see, oh, it's okay. So I think it's okay. I think it's wired correctly. If you want to just sort of straighten that wire and then maybe change those so that they're, but you know, since it is taking a while, maybe just straighten that wire and plug it in and just go with it.
Okay.
And then do your measurements, because you got to do the nodal mesh analysis too. That's part of the lab. You got really good results? Yeah, very good. That's what we want. So you have a good bird board.
Cool.
Yeah. So wrap that up quickly and then do the nodal mesh. That's the
Where do I click these on?
To do what?
To measure V1, V2, V3.
The node voltages?
Yeah. At the node?
Yeah, but remember what the node voltage means. The node voltage, this one means this is the node, this is the voltage of this thing relative to what?
Everything around it.
Sorry?
Everything around it.
What do you mean everything around it?
This and this?
Nope.
No?
We call this node 1, and that voltage is relative to what?
I would assume this voltage source there and the resistance.
Nope.
You know?
It has nothing to do with those.
Then
What
I
we
have
call
no
node
idea
voltage is
what
relative to the reference node, which is ground. The reference node is arbitrarily chosen to be 0 volts. It doesn't. We don't know if it's 0 volts or not, but it's there's our reference node. That's what we're calling 0 volts.
Okay.
And when we have labeled this thing V1, that means the potential difference between this node and ground is V1 volts. That should tell you how to hook up the voltmeter. See how my fingers are arranged?
Well, where do you click ground into?
Well, what does ground mean?
0.
So which node is considered 0?
Off the breadboard.
No. According to my fingers, which finger, my middle finger or my index finger, is connected to ground?
Your index finger is connected to ground.
You're right. That one, right?
Yeah.
So that's where
Yeah, but
that's where the common wire goes for your voltmeter.
But where is that?
Well, on your circuit, you have a reference node. You built this thing, right? Don't you have the correspondence between this part on your schematic and your breadboard? Do you know where? Can you point to me where that is? Should you have that figured out? Yeah. So this is this whole line here is all at your reference voltage, right?
Oh.
So the voltmeter has to have the what's called the common side. Common is going to your reference, and then this is your this is going to go to V1. And when you do that, you're going to measure V1 volts.
Okay, and then you do that for 2 and 3 as well?
Yeah, so basically once you attach this to the reference node, this wire, black one to the reference node, then you can just probe the other node voltages by moving the red wire to the different points of your circuit.
Okay. That makes more sense.
Good.
So I'm not sure if it's right or not. I don't know.
Okay, so look it over.
Yeah.
All right.
Yeah.
Well,
Next one there?
I can see one thing right away. Pencil. Yeah, pointer. This will work. So remember, in any 5 pins that are connected alongside each other like that, those are the same node.
Okay.
That's all one node. And when you have a resistor going up and back to the same 5 pins, you have a resistor that's connecting to the same node on both ends. So if I did have a pen, or here's one, you would say that your R1 is actually somehow connecting like this. Going right back to the same node. And you are also grounding. So this essentially is your reference node, right? That's your reference node. That means what you actually really have is something that looks more like this. And your R2 is doing the same thing, by the way. And your voltage source is also being shorted out. You're sort of applying 12 volts across ground and ground. So you're going to short out your voltage source because you've basically attached the plus and the minus leads together. See what I'm saying?
Yeah.
You're doing that to all your resistors. So those need to be reconfigured. Okay. You might want to walk around and see how everybody else is doing it. Everybody's doing it differently, and you can learn a lot just by looking at a lot of examples.
Resistance.
Yep.
We don't have to do the ground, right?
When you measure the resistance, you don't have to do the grounding. When you measure the resistance of a resistor, you should pull it out of the breadboard. If you haven't measured it yet,
I already measured it.
did you measure it when it was out of the breadboard?
Yeah.
Okay, then why do you want to measure the resistance again?
So does that mean? Oh, that you just copy
Actual
that?
R in table
You
one.
just copy that?
Copy that from table one.
Okay, and then the voltage across R is what we already measured.
In the circuit. Yeah, that's your measurement.
We measured that already. V1, V2, V3. Or is that different?
It's
Oh, it is
different,
different. It is different.
right? It's the subtraction of the two node voltages, right?
We're probably gonna like figure it out. Like,
So if you want to measure the voltage across R2, it's V2 minus 0.
So you
But the voltage across R4 is V1 minus R3, V1 minus V3.
and wouldn't
It's a
it also
potential
be this-
difference.
this
Sorry?
too?
What?
Wouldn't that be included? Oh no, never mind.
I mean, yeah, depending on the polarity of what you want, right? If you want to measure the voltage across, you want to call this a V4 because there's no node V4. V4 would equal V1 minus V3.
V4 would.
The way I've labeled V4 with the plus on the left and the minus on the right, it would equal V1 minus V3.
Okay, yeah. V1 minus V3. Okay. But to measure it,
You're just going to calculate the current. You don't have to measure the current. Or to measure the voltage.
Measure the voltage.
Yeah.
Measure that. So let's do for R4.
I mean, if you've got the node voltages up here,
Yeah.
I mean, you could measure it by moving your voltmeter, so it's going across there.
Where?
You know,
Oh.
put the red here and the black
Oh
there.
wait, that's what you do?
Yeah, you could, but
Oh.
you're going to get the same number. You should get the same number if you measure the voltage here like that. You should get the same number as you do if you subtract your node voltage for V1 minus the node voltage for V2.
Okay. So I might as well just measure.
So right now it says minus 14.76 volts. If you take your V1 value, I think I'm on my computer. Your V1 value, which is, what is it? Minus
V1 is-
2.512,
yeah.
and say minus the V3 value, which is 12.24. What do you get? Minus 14.7
around there.
something, which is what you see right there. You can see that.
Okay.
There's a potential difference between those two node voltages.
Okay. And then, so that was for R4.
Good.
Yeah, I'll probably have another question then.
Let me get over there. So good. These are good high-level questions, right? So you got everything to work out okay?
Yes.
And your question is what?
So this one's receiving negative voltage, negative 2.4, I think. But it's connected to the ground or to the negative lead of this source, and then to the ground of this source. So it's not necessarily connected to any positive power. So it's still getting power because it's connected to the negative leads. Or we're seeing voltage.
Yeah, a lot of interesting questions there. How is the resistor getting power when, given that you have a negative voltage at V1, right? So in other words, you found that V1, why is that so washing out? V1 has a voltage of what, like minus 2.5? And I think it's this black surface that's kind of throwing it off. Let me put it over here. Let's see if that helps. Yeah, I think that's a lot better. So that is that, and this is 0 volts here. I guess my hand is washing it out. Okay. Focus. It's not cooperating right now. So, but what's the voltage drop? So if I asked you what is the, the voltage drop across this resistor.
So it is negative.
Yeah, it's negative. That's the same V1, right? Well, it's the same as saying, well, you've got a 2.5 volt drop this way, right? So which way is current going through the resistor? It's going up. And the power is I squared times R, or V1 times I, using the correct sign convention. I times V is power. So it is dissipating power. It's just interesting, and because these voltage sources are not connected to each other, it's interesting to realize that everything is sort of reaching some equilibrium state, given these potential differences that are driving currents around it. Right? We don't really. It's hard to visualize why that's happening, but we could sort of think about, well, why would you can sort of think that, okay, well, if you're talking about this being the reference node, right? This node here is going to be 12 volts no matter what, right? So most likely there's going to be some drop. Most likely current's going to be flowing that way through R3. I don't know if you confirm that, right? So this is going to be some lower value, right? And then this has to be 12 volts. One has to be 12 volts below 2, right? That's a floating node. That's the new super node you have to use to solve that, right? So it kind of makes sense if you think of it as sort of, water flowing around downhill and stuff. You got going uphill 12 volts here, and then it's sort of dropping some, and then it's got to drop another 12 volts. So if it dropped a little and then dropped another 12, this is going to have to be below this point here, right?
Okay.
I mean, this is going to have to be below ground, right? Because you dropped a little to get to here, and then you dropped 12 more, right? So this has to be less than your reference node.
Okay, that makes a lot more sense.
Yeah, it's a great circuit to kind of really think about what's going on in these things.
Yeah, I wasn't thinking about the high potential aspect of it.
Yeah.
So that's cool. Thank you.
Good. Thanks for asking.
Super mesh.
So yeah, you've got you do have to do a super mesh here.
For what I drew here, that's super mesh.
Yeah, that's a super mesh. Yeah, you can do that.
Okay.
And this is just a known, so this current, what is that, I1?
I1.
That I1 equals 4 amps.
Oh, right. Yeah.
It's the only current
okay,
going through the outer branch.
Okay, but the other ones, or
The other ones
this one
are unknown. I4, that's a voltage source, so you don't know that. I1,
my bad.
voltage source. But this one, I3, I1 minus I3 equals whatever that is,
Okay.
1 amp. Yeah.
Okay.
So it's just drawn funny, but it's not that
This
much
one was
different than
this one was pretty busy too.
where are the sources? Oh, it's just one 10-volt source.
Just a lot of writing.
Is there something that went up here? No. Oh, you took out the
Well, yeah.
because the super mesh doesn't need that, right?
Yeah.
Yeah.
I noted it, but I didn't
Yeah.
Is that okay?
Yeah, but then the by inspection thing is that no, I2 does not equal I1.
Negative I1.
No.
You sure?
Yeah.
Because I got the right answer.
Well, I look at this and say, you can get the right answer maybe, but by nefarious means. That's this thing was settled down. It's looking really strange. I guess my hand is too bright. I need a black glove. It washes out for some reason. It reflects too much. Let me just do it here. So I could move the pencil in it. It'd probably be okay. So what that says is you've got I2 going up and I1 going down. So I2 is going in the same direction as 2I0. So I2 minus
maybe I wrote it
I1
wrong.
should equal 2I0. That's the by inspection equation.
Wait, I have that. But I combined it with that.
I guess. Did you find something? How did you know that what about IO? Where's IO? That's that current there? IO is minus I1.
Yeah, so I combined that.
Oh, I see.
And I got that, and then I got that.
Okay, well that would have probably be okay. Yeah. All right.
Okay.
Yeah. That's what I like to do. That's how you get people's attention.